Okay, I think that's enough theory. And before we move to the lab, do you have any questions related to what we have discussed before? Okay, so I think we have half an hour before lunch, and it's quite enough time to do the first lab. So the lab sheets, they are written in such a way that you should be able to do it yourselves. But we will go through the main things beforehand, so that you can do it smoothly. So the circuit of interest is this one. So on the high level, we have Z-board platform. And on that Z-board platform, we have a chip. And our goal in this lab is to synthesize an extremely simple circuit, which is a wire and an inverter. So we have two inputs. So each input is just one voltage level, 1 bit, and we have two outputs. So the inputs are connected to the slide switches on the board, so that we can play with them. And the output can be observed with diodes, light emitting diodes. So the idea is that the first switch is connected directly to the diode, so that we can control it directly. The second switch goes to the diode via inverter. So if we put 0, we will see 1 here, and vice versa. And we want to describe this particular circuit using VHDL language. Yeah, so this is the board that we'll be using. So the platform itself is here. So this is a zinc platform from Xilinx that has FPGA logic inside. In this lab, we will be using these slide switches that are routed to this chip, and we have a corresponding diode next to each slide switch. So the idea is to program FPGA and see if the behavior of the circuit is the one that we expect. Yeah, in addition to zinc platform, we also have DDR memory here, external RAM memory, but we will not need it. Regarding communication and powering board, so the cables that you will need to connect are the power. I think it is already connected. Then next to power, you have JTAG, USB JTAG cable. JTAG is an interface for debugging and programming FPGAs. So these two sockets that you will need, power and JTAG for programming. And we will use Ethernet for the third lab, but for now only power and USB JTAG. VHDL code is already given to you. The main goal for you is to familiarize yourself with Vivado environment, to go through the stages of design flow and see how it works in practice. And regarding software installation, for the first lab, we need only Vivado to be installed, so you don't need ProtIP or any other external software, no MATLAB. So if you have installed at least Vivado, you should be able to do the first lab. I will quickly go through the VHDL code before you can try it yourself. So any regular piece of VHDL code consists of 3 parts. It is quite strict. So we have, initially we declare libraries. In this case, we use standard IEEE library. It is a standard VHDL library. And we will need a standard logic data type from that library. Then what we do next, we define circuit interfaces. In this case, we have 2 interfaces, 2 inputs and 2 outputs. And we define them. So we have 2 bits from 1 to 0. And 2 output bits again from 1 to 0. And these are just vectors of bits. So it's a bit sequence, and it doesn't mean anything. So you can interpret this bit sequence as a number, or maybe you encode any other information. It's just a sequence of bits, and we are not talking about numbers at this point. Anyway, on the circuit level, you have only signals, and humans and computers interpret these bits as numbers, but this is just a physical process. So, and then we then we define the architecture of our circuit. So this symbol means that we physically connect the first input, the 0th input to the 0th output. This is not assignment operation. This is not happening in time. It's not like at a certain moment you have assigned input to the output. It will be physically connected. The input will be physically connected to the output, and it will always be the case. So it is, once you program FPGA, it is connected, and it's not a software operation. And you can't change it after you program FPGA. And another input is connected to the output via inverter, which is, again, you have a bunch of transistors between input and output to invert the signal. But again, this is a physical connection, and it is not happening in time. It is always there. Once you program your FPGA, this connection is done, and it is there. Yes, so now I think I suggest you start the first lab, and after lunch I will go through the process of through the flow of the first lab, so that you can see. But for now, I suggest you do it yourself. And
so what about the connecting to the Z board?
For the first two labs, I suggest that you stay here, and we will be moving around with the Z boards, because the testing process is relatively quick. But for the third lab, I think that will be in the afternoon. It would be better to move outside, where we have more space. We have sockets on the tables, and it will be easy for you to work in groups. So I think for now we stay here, and after lunch we move out to the library. Okay, let's move to the second lab now. It is slightly more complicated in the sense that now we have certain computations involved. So in the first lab, we were dealing with signals only. So these signals, these are voltages. They don't mean anything in terms of math. So they don't represent any numbers up to the point when we define the meaning of these signals. So in this lab, we will synthesize an addition circuit. So this is addition circuit that we are synthesizing that accepts two inputs, so two numbers, 4 bits each. So as a result, we get addition result, which goes to flip-flop. In this implementation, we'll be using flip-flop in order to synchronize our circuit with other circuits within this within the same top-level circuit. So here we have again we have the Z board. On the Z board we have zinc platform, and now we have a bit more complicated circuit that consists of adder itself. So this is our circuit of interest. In addition to that, we want to use organic LED display in order to show the computations results. And to do that, we use another two circuits, this one and this one. So the bottom circuit is responsible for resetting the display. This is something that normally happens automatically, but when we do this on a hardware level, we have to take care of these low-level details. So we have a circuit for initializing the display and a circuit for printing computations results. So we see that the output of our lab circuit goes to another circuit that actually prints the results on the display. So we have, in terms of interfaces, in terms of upper-level interfaces, in this lab we use slide switches to represent numbers. We have 8 slide switches in total, and we can use 4 switches per each number. In addition to that, we use push button to reset the display. Once you do programming, you might see some random pixels on your display because it is not initialized yet. To fix this, we just press reset button in order to clear the display and to be able to represent our computations results that we want. Okay, so we'll be mainly focused here, but we keep in mind that we have several circuits, and we have this top-level circuit that glues all the components together. I will go through the code for addition circuit. But if you have any questions regarding the whole hierarchy, please ask, and we can consider some of the parts of this code in detail. Again, similar to the previous lab, we have a piece of regular VHDL code. By regular, I mean this is the actual circuit. This is not a library. This is not something to be used later on. This is something that we are synthesizing, and we are intending this for real hardware implementation. Again, we use the same libraries, and in addition to that, in addition to logic library, we use numeric package. The reason why we use numeric package is because we want to interpret bits as numbers. So the same bit sequence can be interpreted in different ways. So that is why we need a package that will help parsing this bit sequence. In terms of interfaces, we have two inputs, one output. Note that the output is 1 bit longer compared to the inputs. This happens because we might get overflow. So the resulting number might occupy additional, most significant bit. And we handle this either by increasing the output signal, or by adding this what we call carry bit that indicates overflow. And in addition to data wires, we have clock signal, and we need this in order to synchronize our circuit with the rest of the circuit. So if we want to make our circuit a part of a larger top-level circuit, which is usually the case, normally we have this hierarchical design, we usually use clock signal to synchronize our circuit with the rest of FPGA. So in terms of architecture, we have this top-level module called process, and so it starts here and ends here. So process. So this piece of code is dependent on the clock signal. So after the keyword process, we have something called sensitivity list. So all the signals that are listed in the sensitivity list, they are continuously monitored by our circuit. And once something happens with the clock signal, then all the code inside the process is updated. So let's say if we have a clock signal that usually looks like this. If we stay on a low level or on a high level, nothing happens. But once there is change, so once there is change of the signal that is in the sensitivity list, so we have two types of changing. We have rising edge, we have falling edge. Then we want to then our circuit will be updated. So once there is a change, we check what is the current state of the circuit. So there is some event, and we want to check what is the current state. So if something happened and the current value is 1, that means that there was a rising edge. If something happens, if the change happens and we know that the current value is 0, then that means that there was a falling edge. So since we are looking for logic 1, so that means that our circuit is synchronized based on the rising edge. So this means that every rising edge so this is our clock. So every rising edge, the input is taken and the output is updated based on that input. And the distance between rising edges is defined by our clock frequency. And I think we use the default value for our clock, which is 100 megahertz, which is significantly lower compared to what we get even with low-cost microcontrollers. And so every rising edge, we do the following. So we take two inputs. In order to match the size of the input and output, we concatenate our inputs with additional 0 in the beginning. So what happens, let's say we have two numbers. Okay, two numbers, and if we perform addition, let me change this to this. So what would happen? So we add it bitwise, and in the end, our result is larger than we have bits in the inputs. So if we don't handle this explicitly, we will end up with overflow error. So we lose our result. It's not only about losing precision, so we get completely wrong number. That is why we want to allocate additional bit, and we augment our inputs with the zeros, which do not affect the result, but it just makes it fixed, the input and the output size. Okay. So we have two inputs, two bit sequences, and we want to interpret these two bit sequences as unsigned numbers. So this is, we can have different conventions. How do we interpret this bit sequence? So we say, let's consider this as an unsigned number. This means that we have, for every bit, we have a certain weight. So, and based on the power of 2, we can calculate the decimal number. So we interpret. This is not conversion. This is just about how would you decode these numbers. So then you perform calculations, and since our output is also a logic vector, we want to perform conversion back, and this is how we get our output. So the difference is that the question.
Yeah, I just wonder why in the if statement there is an event check, while I thought that the process was only happening on the event.
This is a convention. I don't know if this check is redundant or you really need it. I haven't tried it without event, but it might work, but I'm not sure if it is reliable or not. Again, we use the same Z board, and what we want to get is that we want to synthesize this circuit in the same way that we did before, and then we deploy this on the Z board, and we want to play with the slide switches in order to see the result of our computations on the display. But before we do this, I would like to go through the project, through the Vivado project, and show some of the features that you can exploit. So we start. So again, we start with the source pan. So in the same way you did in the first lab, you add these source files to your project. In this case, you have hierarchy of circuits. You have, sorry, you can see it. You have a top-level circuit, and then your adder and some auxiliary circuits that will help you with visualizing the results. So once you go through you can't really see the navigation pane. So let me have a check. So if you go to RTL analysis tab on the navigation pane, so you should be able to visualize your circuit using RTL, which stands for register transfer level representation. So with RTL representation, you can visualize your circuit, and here we can see three main subsystems. So this is our adder. This is, I think, printing circuit, and this is for initialization. And we have some wires to glue these circuits together. And we can zoom in into the circuit of interest, which is this adder. And we can see, this is the same circuit that we were expecting. So we have two inputs going in, the addition circuit and flip-flop. We have 5 flip-flops in the output. So this is how our circuit looks. And this is RTL level. And this representation is not specific to any hardware. It's just a convention. How do we represent this circuit? But if we go further to... So now I will go further to open implemented design stage. I have already opened it. So you should be able to see your circuit layout. So this is our circuit, our Zinc platform, and it has ARM processor on this side, and FPGA logic is the remaining part. And so this is the physical chip, and we can notice that our circuit, so these blue bits here, is implemented on this part of the chip. So it is physically located there, and we can zoom in. So this is how our algorithms looks like in silicon, and if we zoom in further, we will be able to see the actual lookup tables and flip-flops that are used. The only thing that we can't see is connection between them, but I think this information we wouldn't be able to see. There will be too many wires, and it's difficult to analyze. But otherwise, we can see these multiplexers, flip-flops, lookup tables. You can physically see where our circuit is located within the chip. And if you want to see a particular part, you can highlight the wire of interest on the left. Yeah, and you can see connections, and if you need to analyze your circuit. But this is too low level. Normally you won't need this. So you can analyze it and fix bugs if you have some. Maybe you will see bottlenecks based on this. But normally we don't go to that low level. This is just to show that the circuit, it is not on CPU. We have actual transistors, lookup tables that are responsible for the behavior of our circuit. So again, if you're looking for something, you first find this in the Netlist Explorer. If you want to find particular your adder, and then you highlight it here. Because in this case, the whole circuit is mostly used for visualizing the results, while the adder itself is relatively fast. Because addition for integers is just lookup tables, so we need one lookup table per bit. So it is relatively simple. Let's see if there is anything else. Yeah, I think that's it. So this lab will be similar to the first one, but I suggest now when you go through the steps of the design flow, you pay attention to the intermediate stages. You see what you get on the RTL stage. So firstly you check high level description of your circuit. You synthesize it, see what is going on. So it might happen that your circuit will be placed somewhere else in the chip, not in the place where I showed. Because on the underlying level, Vivado uses non-deterministic optimization. So you might end up with having circuit in a different place. but normally it's trying to optimize to have the shortest route. So what we call synthesis is converting VHDL code to RTL level and then to lookup table level. But the way how we really physically place it on the chip, so which particular lookup table will be used for what, this is what we call routing. So how do we place these blocks and how do we route wires between those logic blocks. This is what we call routing, because when you see a report, you might see something like synthesis is done, routing, implementation. So this is what stands behind this. Yeah, any questions at this stage? But I think you should be ready to start, so you have everything you need. The third lab, I would like to cover the most common questions that were coming from the second one. And most of the questions were related to constraint files. So in addition to VHDL code that we add in the source pane, we also supply Vivado with this constraints file. So what does this constraint file about is these are additional directives that tell Vivado that we want to satisfy certain timing, routing, or other constraints. So in this case, we have only used routing constraints. So the main idea is that you have your circuit, and it is described in VHDL, and this circuit has certain interfaces. And in order to test your circuit, you want to map interfaces of your circuit to the physical pins of the chip. And constraints is the way of telling Vivado which interface of your circuit must be mapped to which physical pin of your chip. So what do we say here? So let's consider, so the first group defines the mapping between your, let me have a look, yeah, between your circuit interface, which is these variables here, and the physical pin of your chip. So you have your circuit interface on the right and the physical chip's pin on the left. In addition to that, we also have to specify the voltage level. So in this case, we are using 3.3 voltage with CMOS technology. It doesn't really matter, so 3.3 volts is usually enough to run the interfaces, to run our diodes or display. But the question is, how do we generate this file? And one option is to do it manually, but using the graphical interface of Vivado, what we can do, so we go to this corner and select I/O planning, input-output planning here. And this is the layout of our chip, not really the layout out of the chip, but what you would see on the bottom of your chip. So you might have noticed that you have radiator on the top, then there is a chip, and the chip is sitting on the board with these connections. So we have rows and columns, we have letters for rows, numbers for columns, and this way we can select the pin that we want. And if you are using Z-board, you will see that next to each diode or next to each slide switch or push button, you will see the corresponding code of corresponding chip pin. So there is a routing from, let's say, from your slide switch to the chip, and you can see the number of corresponding pin on the Z-board. And what you do, so you go down here and in order to find your circuit. So this is all ports of your circuit here. And what you do, let's say you open the interface that corresponds to your switch. You define the technology. So we use 3.3 volts, and you define the pin that you want to assign to this interface. And once you do it, your constraints file will be updated, and this is the way how you how you map pins of your circuit to the pins of the chip. So this is what we call circuit constraints. So this is the physical constraint, and often this constraint defines the location of your sub-circuit within the chip. So normally Vivado tries to put your circuit as close to the pins that you are using as possible. Yeah, that is all for constraints. Any other questions in relation to the second lab? I think many of you managed to do it. Yeah, I know you had a predefined set of steps that you have to do, but I think you have enough knowledge now to explore a bit, to change the code, maybe to change the constraints. You will need a bit of patience, because one design iteration, so the time it takes between changing your code and absorbing the results, it's not that fast. So comparing to software, when you get error message immediately, here you have to be a bit more patient. But you should have enough understanding now to try to modify your code and to do other stuff. And now we will be moving to the lab 3, which is okay. So up to now we were working on this level, on HDL level. The third lab is about high-level language, about C, VHDL code generation from C. Okay, so we are making a very big step from 2 integers addition to full MPC formulation. Yeah. This information is this part is mainly based on yesterday's presentation by Michal. So we have a plant, which is a chain of masses that are connected via springs and dampers. So the first mass is also connected to a fixed wall. And what we are trying to do, we are trying to stabilize this system. We assume that we start from a certain non-zero initial position, and we want to stabilize this. We have 10 masses in total, which means that we end up with a model with 20 states. So for each mass, we have its position as a state and its velocity. And we measure position with respect to the equilibrium. So that is why we're considering regulation problem rather than reference tracking. So we want to make all the states equal to 0. In this case, all the position, all the displacements, and all the velocities will be 0, and this means we have stabilized. So, and in addition to 20 states, we have 10 inputs, which are our forces. We can apply force to these masses in order to solve our regulation problem. The objective function is quadratic. And in this case, we use, I think we use terminal penalty the same with intermediate penalty matrix. So we have a quadratic objective. So we want to regulate our system around the origin. We start from a certain non-zero initial condition. We have our dynamics. And the only thing in terms of inequality constraints, the only thing we have are the input constraints. So we don't consider any other constraints. We don't apply any bounds on states, only input. And we assume that these are upper and lower bounds. So what we do with this problem, so we do condensing. So we eliminate the states, so these states, from decision variables. And we end up with a dense QP. And the decision variables for this QP is our input. So coming back, so we have eliminated dynamics and initial state from the formulation. So this goes to the objective. And then we have only inequality constraints, so which are these. And since we are doing condensing, we lose sparsity, and we end up with a dense Hessian and a gradient vector. Yeah, and this is although I didn't show it on the slide, so this is a parametric optimization problem. So the gradient vector H is dependent on the current state. So we will update the gradient every step, every sampling instant, in order to solve corresponding optimization problem. The good thing is that Hessian is fixed, and we can pre-calculate some of the matrices for our optimization algorithm. To solve this problem, we will be using a projected fast gradient algorithm, which is an accelerated version of a standard gradient algorithm. In this lab, we don't assume in-depth understanding of this algorithm. So the only thing that we have to understand from implementation point of view is that we have matrix vector multiplication step on the first stage of our for loop. Then we do matrix vector multiplication, which is for calculating the anti-gradient direction. After that, we do projection on the feasible set. So projection is relatively simple. So if we are inside the feasible set, we leave the number as it is. If we're outside, so we either set it to maximum if we are exceeding, or to minimum if we are below the lower bound. And in contrast to standard gradient algorithm, we also use extra momentum step in order to accelerate it. This was introduced by Nesterov's, and this algorithm is also known as Nesterov's accelerated gradient algorithm. So in the end, we have matrix vector multiplication, projection, and extra momentum step, which is vector-vector operation. You should already have a code that implements this algorithm. All the steps, apart from the fifth line, projection on the feasible set, we didn't implement it. This is something that you can improve. So what we did, we just set so the next z variable to the current theta without using any projection. So this is something that you can try for your project. Yeah, maybe some other improvements that you will make. But for now, we consider that there is no projection, a pure accelerated gradient algorithm without any constraints handling. Yep.
Theta is actually the vector of all u
yes.
values?
Yeah, so we don't have current state or intermediate states as in our optimization problem. We eliminate them. Yeah, that is why we consider only inputs.
So it's u0 up to
un minus 1. Yeah, correct. So.
Sorry, Bulat, could you just write the expression for theta on the whiteboard?
So wait, this one.
Yeah. Theta equals u.
Okay.
Yeah.
sorry.
Okay, we'll come back to pipelining later. Now let's see how do we implement this from the point of view of using software. So before that, up to now, in the first two labs, we were using Vivado in order to convert our HDL code into FPGA bitstream, and that's all we did. So we were working on HDL level. Now we are moving a bit higher. I mean, we already understand that implementing even this simple algorithm in VHDL is not that easy. Even integer addition requires some effort. But when we come to fixed or floating point numbers, things become even more tricky. So that is why we use higher level approach. We use another software tool from Xilinx known as Vivado HLS. So this is their logo. You might find this logo on your desktop. Yeah, and coming from the architecture, so we have Zinc SoC, so our Zinc platform, which has CPU and FPGA on the board. So what we will do?
Sorry, could you speak up, please?
Yeah, sure. So what we will do? We will use Vivado HLS in order to convert our C code into VHDL. So Vivado HLS generates both VHDL and Verilog, and but we will be mostly using VHDL. So this is with Vivado HLS. Then what happens? We pass this VHDL code to Vivado, and then Vivado generates bit stream, and this bit stream goes to the board. And in order to handle data transfer between the board and your desktop machine, we will be using CPU. This is only for data transfer, not for calculations. And the CPU will manage communication with the desktop via Ethernet. So this is the general structure of the simulation that we will be running. But before we go to this step, we will do software in the loop simulation when both the MPC C code and the plant model are simulated on the desktop machine. Afterwards, we will come to processor in the loop simulation when you have your algorithm on the actual hardware and you simulate your plant on your desktop machine. So theoretically, you verify it in this way and then replace your desktop machine, replace your model with the actual plant. And in the third lab is very sensitive to the way how you installed your software. And before we start the lab, I would like us to make sure that you have installed your software in the right way. To do that, I would like you to open your MATLAB command lines. So our main goal at this stage is to make sure that our MATLAB installation is aware of Vivado tools. So if you type system and then the name of the tool you are calling, any questions or problems? We will go through, I think I will have to go through the installation instructions again. But so the main goal is to make sure that when you call system Vivado with a system function, you should be able to open graphical user interface of Vivado. Yeah, this is what ideally should happen. And if you are able to achieve this, it is very likely that you will be able to run the remaining part of the lab 3. I will come back to this. So.
Bulat,
yep.
If you write down what they need to type in, we can't see from back here.
Okay, sure. Okay, if you have Vivado installed and if you have done the first 2 labs, means there is on the Vivado side everything is okay. The only thing that you have to do is to add So if you go to this website, you will find, I suggest you don't do this now, because now we will go through the steps of the lab itself. But afterwards, you will have time to do this and go through the lab itself. So if you go on this website, you will find instructions how to modify environmental variables. And the main thing that you should do is to find path environmental variable and add your Vivado installation directory to that path. Once you do this, you should be able to call Vivado from the command line. So it's not that difficult. I will leave this for now. Afterwards, we will be able to help you. But for now, we will go through the lab itself. So what do we do in this lab? Just a sec. I will. So this is the high-level design flow for the third lab. So what you normally initially do is you define your design parameters, like for example horizon length, the number of iterations of your algorithms, and some other parameters. So once you define these parameters, you can generate the state space model for your system. So the reason why the state space model depends on the design parameters is because your discretization, because your sampling time affects discretization. That is why we firstly define the design parameters, and only after that we can generate discrete time state space model. Having the model and QP and weight matrices, Q and R weight matrices, we should be able to generate the main matrices for our QP solver. So what we do in order to speed up the algorithm, we pre-calculate some of the matrices offline. For example, this one, I'm not sure if you can see it. Yeah, so the fourth line, so we have a scaled version of Hessian and identity matrix. So we can pre-calculate this offline. And this is what we do in order to speed up the algorithm. Otherwise, we have only vector-vector operations, and there is not much that we can pre-calculate. Apart from this scalar, from this extra momentum step, we can pre-calculate 1 plus beta, which save us another adder. Okay, then we generate QP matrices. So we have the C code already written, apart from projection. This is a very simple implementation, and there is a lot of space for improvement. So if you are willing to do so for the project, that is one of the options. So once you generate the matrices, you do software in the loop verification. So what happens with the software in the loop verification? So this part is implemented on your desktop machine, and communication between MATLAB and your C code is performed via MEX interface. So you compile MEX file, and then you can do software in the loop simulation, and you will have an idea how good your controller is. So if your software in the loop simulation fails, that means there is something wrong in the code. So you might want to come back. Maybe you want to increase horizon length if you get unstable behavior. and then you go through these steps again in order to get a proper closed loop simulation. Once you do this, then the next step is, so you have your C code at this stage, and you give this C code to high-level synthesis tool, to Vivado HLS, that will convert your C code into VHDL. And after that, once you have VHDL, you convert this VHDL code to bitstream. This bitstream goes to FPGA. And in this case, in order to verify performance, you can't rely on diodes or this tiny display. So you want to exchange relatively large amounts of data. And for that reason, we will use Ethernet connection. So we use UDP protocol for that. So in order to allow computer and the Z-board to communicate. Okay, and depending on the outcome of this simulation, you might want to change design parameters again, or if you're happy, so you stay with that design, and that is your FPGA implementation. I have to say a couple of words about these two steps. They are the most complicated, but fortunately, we don't have to do this manually. So these steps can be automated, and the automation happens with the ProType software tool that we have developed in our lab. The main idea is that you give C code to the tool, and the ProType takes that C code and automatically converts it from C to VHDL using Vivado HLS on the underlying levels, then automatically converts VHDL code to bitstream. Again, you just have to call one MATLAB function instead of creating the project and doing things manually. However, if at a certain stage you want to open the project and see what is going on, you can do this. So you just go to debug mode, and in this case you will open your Vivado or Vivado HLS project, depending on the stage that you are on. And yeah, you can also handle low-level details. If you are not interested in that, you just trust ProType default parameters and Xilinx tools. And then you have automatic software in the loop verification. So all the communications via Ethernet, all these things are handled automatically. And normally, once you get certain experience, if you have everything installed, probably it will take you maybe 20 minutes from a verified C code to FPGA implementation. So while normally it will take several days even for FPGA engineer to do all these things manually. Okay, so we have how many? Seven stages of the design flow. And if you open the main script of this project, of this lab, sorry, which is called the main script, yeah. Any idea how to zoom in MATLAB?
View, I think.
Configurations, you have to
You do it manually. Okay, yeah, so as we have seen before, we have 7 stages, and we have one section of MATLAB script and every section corresponds to one step of the design flow. Okay, so the stages are separated with the double percentage sign comment. So we have 7 stages in total. So what we suggest, so you uncomment corresponding stage, execute the script, make sure you understand what is going on, and then you uncomment the next section, and this is how you progress with your implementation. So for every step of the design flow, you have a separate script, either script or function. So if you, apart from the first one where you just have a structure. So you define a structure in the beginning, you define a design structure, and after that, you based on that parameters, you generate model. So this is done by model generator function. Then you go further, you generate QP, generate headers, H files for your C implementation, and then you go further. At this stage, yeah, I don't recommend uncommenting the whole script and executing all the lines together, because this makes it really difficult to debug. So I would suggest you go step by step. Yeah, and up to the synthesis stage, you will not need the Z board. So up to here, up to synthesis, including synthesis, you don't need anything apart from your laptop. And for the last step, you will need to connect Ethernet cable and power on the Z board in order to see how it works. So you see, in this case, you don't really need to open Vivado graphical user interface. Everything is handled internally. So if you are interested in internal operation of ProtIP, I would suggest you go to HLS and synthesis scripts that call ProtIP functions internally. So that's it. So ideally that should work, but of course we expect some problems, and I will give you some tips to handle this, starting from the installation. So as we have discussed initially, we add these environmental variables. What we do next, we download ProtIP from GitHub. After that, we add a couple of other environmental variables in order to let Vivado see ProtIP. Then we go to Vivado in order to, I mean, this is all available on the website. I'm just going through the steps again. Then we go to, once we have downloaded and configured environmental variables, then we go to Vivado in order to install ProtIP. So it is available on what they call Xilinx Tickle Store. So it is a repository for software applications that help FPGA engineers automate their designs. So you will download it. After downloading, you will install it, and then you should be able to use it. And the final remark regarding installation is configuring Ethernet interfaces. So you have to assign a static IP address to your computer. So this is a standard address that you often see for the local networks. And the way how you do this is explained on this website. You should follow the link. It will take a couple of minutes to do. It's a standard operation for Windows. That's, I think, all regarding installation. And let me see if there's anything else. And if you want to learn more about coding in C, so that you can tailor your algorithm for efficient hardware implementation, I suggest you go to Vivado HLS user guide, or you might have a look on this for this presentation. So they give a brief introduction to the tool. And regarding ProtIP, you can refer to Wiki if you want to use non-standard features, improve your design. I would recommend you go to the Wiki page, and you will find documentation and other useful information. And I think I will also go through the C code. So this is a standard C code, apart from the directives that you provide to the compiler. So in this work, we will be using only pipelining, pipelining technique. So we know what pipelining is. So it is in relation to C code. This is a common approach for speeding up the loops, so that still you have, let's say, moderate resource usage. And it's in contrast to parallelism, when you physically parallelize computations, when you have to synthesize logic for all the branches. With pipelining, it works more efficiently, and you will see. So you see these pipelining directives almost in every loop. Yeah, you can try executing your code with these directives. You might want to comment them out to see what is the effect on performance. You might want to go to Vivado HLS documentation and add your own directives to see how does it affect performance. Yeah, and there are many things to explore. So once you go through that design flow once you make sure it works, then you have a lot of things to do in terms of improving, in terms of exploring other possibilities to see how does it affect silicon usage, how does it affect execution time of your algorithms, and other things like this. And I think that's it for the third lab. This is the last lab. And now we are starting the practical session, and we are happy to take your questions. Yeah.
Just a small question. The bounds or theta are in the header?
Yes, so they are available. Wait, yeah, I will.
Can we directly refer to the name or not?
So you have this QP matrices header.
Yeah.
All the matrices are there. You have design parameters, like scalar parameters are here. And so
you can just directly refer to the name.
Yeah, well, this is projection loop. You see it does nothing, but just it does not actually project. So
we use there the variable u max. The program should recognize it because it's in the header.
Yeah, so if you go to the header file, QP matrices, so you have umax, umin. Yeah, sorry about the confusion with the names. So yeah, umax, it is actually the whole theta vector, but theta is essentially u.
But just like these variables are defined in the same way that if they were defined in the actual C.
Yeah. So the only thing that is changing the loop. You don't need to change H file generation, things like this. Yeah, and note that H file is automatically updated from the script, while CPP file is, I mean, it's up to you how do you modify it. Yeah. Yes, please.
Is there any particular reason why there are go-to labels used in code? Or is it just for documentation?
It's not really for documentation. The main reason why we use this is that when we see the report that comes from the synthesis tool, normally the report is given based on the labels that you provide. And then you can see like, okay, this loop was pipelined, this loop, like, sometimes Vivado says that I was not able to pipeline this loop because of data dependencies. So it's good to develop this habit of giving labels to loops. And yeah, it makes code clearer. And yeah, once I started working with FPGAs, I developed this habit. So instead of putting a comment, I would rather put a label, because then you have clear warnings and errors report, and you know which loop caused the error.